Today we have Tafer Seholahi. I probably butchered his last name. Sorry about that. Who will be talking about ultra diffuse galaxies. We're on a free Zoom account. So you notice in the email there are two links. If this happens to go over 40 minutes by any chance, then we could just go ahead and switch over to the second link. All right. Go ahead and give it.
Okay, I start to share my screen, sure. Do you confirm that you see it?
Yeah, we can see it.
Okay, so thank you, Brian. I hope you all are fine and start the week in a very good way. So today I'm going to talk about a galaxy, an ultra diffuse galaxy, Dragonfly 44, which in the last few years, it was known to be a bit anomalous. However, recently we published a paper with the help from my main supervisor, Captain Rainier, and our collaborators in Tenerife. And simply we showed that this conclusion is not really accurate. So the story of ultra diffuse galaxies starts a bit earlier, when there were known with different names. People knew about low surface brightness galaxies and referred to these objects sometimes as extremely or very low surface brightness objects. And from that time, people found these kind of objects in galaxy cluster each time, maybe a few of them. And since that time, they had these questions like, what is the distance of these objects? And what are the physical diameter, what we can say about the dark matter content of these objects, because they are quite diffuse and they are surviving in the environments of the galaxy cluster. So there were all these questions under debate. However, recently a group led by Van Dokkum in 2015, when they were testing their instrument, the wide field imager they have known as Dragonfly, they were, they targeted diffuse light around galaxies, which shows the assembly of the galaxy. And it was part of a testing of the instruments. And they found accidentally 50 of these low surface brightness, very low surface brightness objects in the Coma cluster. So what they said, that if all these objects are actually in the Coma cluster in the distance of 100 megaparsec, some of these objects, as you see in the right plot, can be even larger than the Milky Way. Milky Way is shown in blue, and y-axis indicates the effective radius of the objects. And you see some of them, the red ones are the new galaxies. They call them ultra diffuse galaxies later. And these galaxies can be larger than the Milky Way. So the question was, if they're larger than the Milky Way, maybe they're also as massive as the Milky Way, but they are faint. They're like 100 times fainter than the Milky Way. They have less stars than Milky Way. Maybe it means that they are sort of phased versions of the Milky Way, that it couldn't transfer the mass to stars somehow. Okay, before going further, I just want to say that when we talk about size, at least in this topic, we always refer to effective radius, which actually measures the compactness, the concentration of light. There are different ways to measure the size of the galaxies. For example, there are definitions based on assigning an age to a galaxy based on surface brightness. Okay, in that sense, these galaxies are not actually really large. Anyway, so things started in 2015. That more attention UDG got more attention after the work of Van Dokkum. People started to search more deeper in other nearby galaxy clusters and galaxy groups. There have been works in Captain within Rainier's group, and nowadays there are more of these objects found everywhere. But the question was, the most important question at that time was, how massive are these objects? Or if they are actually like Milky Way, if they are failed Milky Ways, they should be as massive as Milky Way. If they're not, if they are somehow a dwarf related to dwarf galaxies, they should be as massive as a dwarf galaxy. So mass measurements was quite important. One of the first works studied VCC 1287, which based on the new definitions, it was now an ultra diffuse galaxy, or UDG. They could, for UDGs, because the light is very diffuse, doing a stellar kinematics for deriving mass is not really easy. The authors of this paper used global clusters and the dynamics of global clusters to derive the halo mass and the total mass of the object. And what they derived was about 10 to 11 solar mass. It means that the galaxy is still dark matter dominated, like faint dwarf spheroids in a local group, but it is not as massive as the Milky Way. So the idea of failed Milky Way cannot be correct, at least for this object. Then one of the conclusions of the authors of this work, it was that interestingly, you can also use the correlation between number of global clusters and the mass of a galaxy that people already knew for other galaxies, and derive the mass or estimate the mass of this type of galaxies as well. So next years, people try to study more of these ultra diffuse galaxies. Each time with SR kinematics or GC kinematics, they studied 1, 2, 3 objects. It was really uncertain, it was time consuming. Then at some point, people started to do photometry, do imaging, deep imaging, and actually have a bigger sample of these objects to have a more general view of this type of galaxies. So in that sense, when we talk about, when we want to measure the mass, we count the number of global clusters. And sometimes people don't talk about number of global clusters, but they talk about specific frequency, which indicates the efficiency of a galaxy to form global clusters. It is the number of global clusters normalized by the luminosity of the galaxy. So for typical dwarf galaxies studied before, the black points in the diagram, and for UDGs, at least in 2 studies in Coma cluster, the other colors like the pink one and the reddish ones, uncertainties are large because the number of global clusters is still really low. That leads to these large uncertainties. But in general, people started to say something about the specific frequency of the general population, that it is a bit larger than the normal dwarf galaxies. Some studies found this, some studies didn't, so it's still a matter of debate. Anyway, on the other side, there was also groups around the world trying to actually produce these objects in galaxy in simulations. So, and they could produce the similar galaxy with similar photometric properties, morphology, surface brightness, sizes, and all in these simulations, the scenario that they implemented was some of these objects can born well in the field, and because of the supernova explosions and the feedback, the outflow from this explosion, the galaxy puffs up. Then some of them can also have early infall into galaxy clusters, and the quenching happens a bit earlier than the other galaxies that fall into cluster later. So for the same amount of mass, they have less stars, and also the tidal interaction led to this puffed up features that we see. So it means that there's not one scenario, but there are a couple of them, and all this scenario relates them to dwarf galaxies, to dwarf population. When I'm talking about dwarf population, I'm talking about 10 to 11, something like the upper limit for Large Magellanic Cloud. But again, we're back to some years ago when Van der Kolk studied, found these objects in the Coma cluster. Dragonfly 44 or DF44 was the biggest, the largest one, the term of effective radius. And it is not really surprising that they wanted to, if they want to study these objects, they go for the largest one because it can be more exciting. Then they studied these objects in different works. The first work, actually, they confirmed the membership of the object, and the object is inside the Coma cluster at the distance of 100 megaparsec. Then in 2016, they measured the mass using a slit spectroscopy. They derived, and based on some assumption on the profile of the dark matter, they derived 10 to 12 solar mass for the galaxy. So this means that with 10 to 12 solar mass for the halo and 10 to 8 of stellar mass, this galaxy is 99.99% dark matter, which is something really different than everything that we observed yet. Then this idea was also supported by the number of global clusters that they found around the object. It was based on the ground-based observations, and they tried to still use that data. It had good seeing conditions, so they tried to estimate the number of global clusters, and this number was about 100, which is also is in the same magnitude of the same range of global clusters around Milky Way. So the conclusion was that this galaxy is a failed Milky Way, and the news was quite big at that time. Later, they used a space-based observation of HSC to count the number of global clusters, because with resolution of HSC, it's easier to distinguish between global clusters at that distance, which look like point sources, and background galaxies, which are slightly extended. In ground-based observation, it is a bit more tricky. So they counted number of global clusters, and the number that they derived was lower. It was around 80, but the uncertainties was still large enough to be consistent with the previous result, about 100 global clusters. But later, in 2019, they did another spectroscopy observations. They studied the slug kinematics, and the mass that they derived was 10 to 11 solar mass, which is now the galaxies in the dwarf regime, in the age, more or less. However, if you look at the uncertainties of the measurements, the upper limit is still high enough to be consistent with the galaxy to be a failed Milky Way, be a large Milky Way mass galaxy. Anyway, so at the end of the studies, there were two ways to look at this galaxy. First, some people said that this galaxy is actually an overmassive galaxy. It has overmassive halo, like as massive as Milky Way, and it is actually a failed Milky Way. Some people said, okay, the mass is 10 to 11. We can, if we trust the main value that they reported in the latest work, the mass is 10 to 11, but the number of global clusters that they derived, like 100 or 80 in other studies, it doesn't match. So this galaxy should be more efficient in forming global clusters. Note that UDGs are known, what I showed before. Some people showed that UDGs have a bit slightly higher specific frequency than other galaxies, but the difference of this object was a bit higher. I will show that later. So the galaxy, as I said, is in 100 megaparsec from us. The solar mass is 10 to 8. Effective radius has been measured in different works. Our value is 3.9, and Van Dokkum measured in different works, and the latest one, based on HSC, was 4.7, almost 1 kiloparsec higher. Then if the galaxy be a normal dwarf galaxy, for this stellar mass, we expect a mass of 10 to 11 solar mass and number of global clusters around 20. So again, I have a summary here of the studies of different years. So the number of global clusters they measured in 2 times is more or less, let's say, around 80. Then the mass they measured, the first 2 times it was quite high, close to mass of Milky Way, but the last time it was lower. However, the upper limit is still consistent with the work from 2017. Also mentioned the specific frequency is something that people talk about it sometimes instead of the number of global clusters. Then if we look at the specific frequency of galaxies, normal other galaxies studied before in this diagram, y-axis is specific frequency and x-axis is velocity dispersion, which can indicate the mass of the galaxy. For Dragonfly 44, the galaxy is far from the other galaxies as being studied. So whether the galaxy is overmassive or it's just an outlier of this specific frequency and mass relation of other galaxies. So these 2 conclusions had, well, there were different studies, but there was one study that was the main idea behind these conclusions, and it was that observation based on number of global clusters with HSC. So we start to ask this question that if we can reproduce this number, if no, why not? Because it shouldn't be just reporting a different number or a number. It should be about understanding why if the number is different, why it's different, and how it went wrong in their study. what is the number that we get, and what are the implications. I also want to say that it was not something that we say, okay, we want to work on it and we want to find a different number. It was, which we will at the end, it was just exploring things at some point, and just shortly after exploring the first results, we found out, okay, this number can be different, and we also had ideas about how it went wrong. So that's why we started to work on it a bit in a more serious way. So now I'm going to work on the same data as the work on 2017, which counted number of global clusters. The data is with HSC in 2 filters, and one filter 606 has a longer exposure time, and we can reach to the turnover of luminosity function of global clusters. I will come back to this later. And this is the main filter for our study. The other one we use for just some colors for the brightest objects. Okay, then we count the number of global clusters. I put it in 3 different steps, and I go through them each after another one. The first step, so okay, before I would say that this part becomes technical because we should understand how the analysis works and what are the differences. That's why it's going to be a bit more technical from here. So the first step, identifying compact sources around the galaxy. It means that global clusters at that distance look like point sources, and what we should do, we just should find point sources and remove all the objects that look to be extended sources. So on the x-axis of this diagram, I have the compactness index values measured from the data. The smaller values means that objects are more compact. Y-axis is the magnitude, and this diagram is the basis of the separation of compact sources and extended sources. Usually there is there can be a clear separation, but not in this case. So what we did was we measured all the compactness indexes for objects in the data, the red points. Then we simulated more than 10,000 artificial stars everywhere in the frame, and we defined this line that I showed here, and everything from this line, every red point source from this line to the left is a compact source for us, and everything on the right is an extended source. However, Van der Kom, in the paper in 2017, they used this line, and everything from this line to the left was a compact source. So there's a small difference between these. There's a difference between these two. You can see between these 2 lines there are some objects. And let's see how this changes our result. What we found based on our selection, the global clusters, the compact sources, let's say, that I found, I showed it here in yellow, and red ones show the objects that Van der Kom selection finds, but my selection doesn't find. So at the end, maybe there is a difference, but this difference is about 50 or 20%. It's not that large, but still there's a slight difference here. The biggest difference is here. When you zoom out and you look at the compact sources selected by both methods, left is what I did based on simulated stars, and right is something that Van der Kom has done. You can see that objects in the closer galaxy that are likely to be global cluster are more or less the same. But when you go further in where objects can be just random background objects, for our selection, there are less, and for Van der Kom, there are more. So that what when I look at this, I would say that our selection is cleaner. Let's see what the implications of this cleaner selection. Next step, I'm going to, so now I have a selected point sources. Next, I want to define, for some reasons, an ellipse or a circle, just different assumption can be made, that contains half of the global clusters. And I define this radius as half number radius. GC is half number radius. So what I measured from my data from my selection is indicated in yellow, and it is actually twice smaller than what Van der Kom used in the paper. Interestingly, the GC half number radius that they measured was similar to the half-light radius of a galaxy, even a bit smaller. And the important point here is that Van der Kolk tried to measure the half number radius of global clusters, but he couldn't. Let's say the group, they couldn't. They didn't find any uncertain value at the end. And what they did, they assumed that this value follows the same relation as other dwarf galaxies. It means that they assume that half number radius of global clusters is 1.5 times half-light radius of a galaxy. And remember, the half-light radius of a galaxy that measured, it was also 1 kiloparsec larger. So at the end, the half number radius of global cluster that they assumed was 2 times larger than the value that we measured. Why they couldn't measure it properly, I think it is related to the selection of the point sources. It was if the background is crowded by contaminants, so measurements can be very uncertain. Then, so when we have the value of half number radius of global clusters, what we do, what I did at least, was I said theoretically 99% of the global clusters should be inside 3 times half number radius of global clusters. Van der Kolk, what they did, they said, okay, the half number radius contains half of the global clusters, theoretically. So if we double it, then we include all the objects. So this part is not really, doesn't make any difference. It's more about the half number radius is different, and they already select everything that is there, and they double it again. Then the third step is to look at the luminosity function of objects that are found. Luminosity function of global clusters is expected to be something like this, symmetric, with a peak that we more or less know where it is. It can be slightly different from more massive galaxies to less massive galaxies. And the thing is, we don't observe all the luminosity function. We see everything to the peak and a bit further. And what we do is we count number of global clusters to the peak. We estimate something based on the symmetric shape of the luminosity function. We estimate the total number of global clusters. So at least we make a correction for the faint global clusters in the luminosity function. So the number that we get after this was about 20. And what we did was not only do things based on one assumption, we did different assumptions. The distribution of global clusters can be like the galaxy, as I showed, it can be an ellipse, or it can be just a circle, we don't know. Selections can be done in different ways. There are uncertainties in the value of half number radius of global clusters, the values of the location of the peak, and so some other uncertainties that can happen. So including all these uncertainties, the values are, the average value is around 20. It's 4 times less. And if you want to put an upper limit, it's still, the value would be around 30 or 40, which is still 2 times less than the Van der Kolk's number. So with this new number, if we measure the mass, the number of global clusters gives us the halo mass. The new mass is very similar to the mass from kinematics, at least the mean value that they reported in 2019. And it brings the galaxy also in the specific frequency mass diagram or velocity distribution diagram to the green point among other galaxies. So it means that this galaxy is not really strange with our numbers. So I'm going to give a summary here. For the summary, I answered the questions that I asked before. Can we reproduce the number of Van der Kolk 2017? No, but we know why. We know that this is mainly based on the assumption that they made about the half number radius of global clusters. And this is simply, it might be correct for other dwarf galaxies, but this is not correct for TF44. The number that we got was 20 global clusters, and it means that this galaxy is like a dwarf galaxy and it's not extraordinary. So with these findings, we also try to reflect it in the media, in the press, and since it was related to dark matter, people also found it interesting. And in October, when it was on, it was among one of the most popular news in the media. So that was it. Thank you. I will be happy to answer your questions.
Thank you. That was a very nice talk. Does anyone have any questions? All right, well, I'll go ahead and ask a question. Can you go back to the slide with the cuts?
Yeah. Okay. You mean this?
Nope, back. There we go.
No.
So with these two different cuts, you kept everything on the right-hand side in this picture.
Yeah, I've removed things that are on the right-hand side.
Yeah, so that brings up two questions. First, what sort of criteria? So you used in your the dark blue line that sort of wiggles here. It's a function of both V and delta M in this plot. What sort of criteria did you use to make these cuts? Why here? Why not slightly to the right, more to the right towards?
It is for example, on the y-axis we have magnitudes. For each magnitude, I found the compactness value that selects 99% of the objects. So this selection selects 99% of the objects. That's it.
Okay.
So another 1% would be on the right.
So you had a number of bins in V and you selected the location of that bin in delta M such that it had 99% were excluded from the simulation, from the artificial stars. Yes. I got it. Now, this light blue line is what was used in this other study, right?
Yeah.
But it's more restrictive for all values. That's what I see here.
Yeah. So yes, that's what they did, and they said that this is probably a loose way to select objects. There was not really good reasoning behind it, that why they use this value in this way. It's just something like more traditional. But then they said, okay, we will correct for background objects later. If we select more objects, we will correct it. But this correction doesn't help that much, apparently.
Well, I mean, my question is, if it's more restrictive, which is what I see here, then how is it in later plots you show they have more data points?
It's not restrictive, it's actually loose. It selects more objects. So let's say the region that I indicated by lines, so the region that is indicated by lines, by vertical lines, is actually the region that is selected.
Oh, you select everything to the left.
The left, yeah.
Okay, for some reason I kept thinking you said to the right. I must have misheard you. Okay, so this is actually...
Yeah, it's just a complicated plot, I understand.
Okay, got it. That makes more sense. Okay, we have some other questions. Let's start with Pavel. Go ahead.
Yeah, thank you. Hi, Timur, nice talk. I have a couple of questions. So one of them is, when you show, I mean, that just because I don't know, maybe I didn't understand, but when you show the, I think it's the next couple of slides, when you show the different RGC that you use compared to the one they use.
This
one?
You
say that, no, yeah, so yes, there.
There's a delay.
Yeah, so I didn't follow. So why did you say that there are 99% of the globular clusters inside that radius, and they say we double this, the number inside? So because you say they may be, this number may be good for their dwarfs, but wrong for EDGs. But how do we know what's right? I didn't understand that part.
Sorry, so I probably didn't understand the question. You're asking, can you repeat your question?
Yeah, because you say, look, we count the globular cluster within 3 RGC, and that's 99% of the expected UDGs, globular clusters in the UDG. So how do you know this?
Oh, okay. This is not for UDGs. This is because we have a distribution, and we have a sort of maximum likelihood solver that finds the best statistics function parameters. So for the derived statistic parameters, statistic index, and half number radius or something, we have a distribution, and the area under like the function before 3 effective radius is like 99%. It's just something based on the shape of the function.
Okay, I see. Thanks. And another quick question.
Yeah.
Because you are comparing with the luminosity function, and you say, look, we know that it should have more or less this shape, and based on the completeness we have, we expect like these numbers. But I know that there are like some claims that even when we observe the luminosity function of global clusters to be basically universal everywhere, I think there are some claims that it may not be universal. I was just wondering if the luminosity function is not universal, how could this affect your results?
So there are differences that we already know. I mentioned that for massive galaxies and fainter galaxies, it can be different. That's something we already took into account. So the location of the peak can be like a point to fainter for fainter galaxies, and we took into account this. Also, it really, if there is a difference in shape of luminosity function of this galaxy, still my comparison with Van de Kom is valid, because that's the correction that we both do, right? So relatively, whatever number get compared to Van de Kom is right, but okay, maybe the shape of luminosity function after that is very complicated. Who knows? That's true.
Okay. Thank you.
Thank you. We have about 5 minutes left on this meeting, so I'll go ahead and go to Rainier's question next. But if we run out of time, we have
Let me speak, then we have time.
Sure.
There's another of these galaxies that Van Dokkum published. It's called DF2, which does not have dark matter. So what are you going to do about that one?
So I personally don't have any plans for that, but there are lots of studies. So for DF2 per se, there is this uncertainty in the distance. Well, it depends. Some groups still believe that it is in 20 megaparsec from us. Some people think it's 13 megaparsec. It's not really clear. But I think we should just wait for the deeper data that they have. They already showed that the luminosity function of global clusters for DF2 is it has two peaks. One peak which is bright, one peak which is faint. I think we should just wait for the theoretical peak, the theory side, if they can reproduce this kind of objects or not. I think it's too early to say anything.
Okay, thanks.
Okay, thank you. What I was going to say is that if we still have a few minutes for another questions, if there are any. If we run out of time, there's a second link in the email I sent out. But are there any other questions? Gabriella?
Yes, so my question is there any meaningful follow-up, for instance, spectroscopic, that one can do to check if some of these objects that Van Dokkum consider globular clusters and you don't consider globular clusters are indeed something else than a globular cluster, and what they are?
Well, there is, in theory, we can always do spectroscopy, but current instruments that cannot reach that magnitude. So you can see in the luminosity function I have here, these objects are fainter than 26. And for that, I don't know, maybe some people plan to do that with James Webb, but with other instruments that we have already, it's not possible. So there is no way to find out, actually, for the moment.
Okay. Thank you very much.
Okay, thank you. Are there any other questions? Nope. Okay. Let's go ahead and give our speaker a hand, and we'll see you in future. See you around.
Thank you.
All right. Bye.
Bye.